In this video, we will learn how to use the principles of least square in order to fit a data using a straight line equation, which looks something like here. So where y is your dependent variable, so y is your dependent variable, and then x is your independent variable. M and c are the constants. So n typically refers here to slope and c refers here to the intercept. So this is a very common expression that you will use in chemical engineering. Most of the data will follow a simple straight line equation. Just for example, let's say you have, let's call it simply yx, which is plotted on the x-axis, and some dependent variable which we label it as y, which is plotted on the y-axis. And you may have data something like this, or maybe something that may look like here, or maybe something like this. So most of this type of data shows that something, in this case y, changes with respect to x, and it follows a linear trend line. Yeah? So this type of relationship that exists between y and x we can use the simple straight line equation. So can be represented using equation y is equal to mx plus c, where m is the constant and is equal to the slope. So what is slope? So slope is nothing but dy by dx, and then x will be typically your intercept here that cuts the y-axis at x is equal to 0. So c is your intercept, y is your slope. So how do you determine this? How to get m and c? So one method is to use graphical method. This graphical method is you plot something, and then based on your what you think is correct, so you simply draw a line, and then from the line you get a slope, and from the intercept you get the c value. But this graphical method has a lot of disadvantages, because who draws the line? So the user. So depending on the user, the results will be affected. So I can draw some line here, another guy can draw a line that may look like this. Yeah, so depending on the user and the experience of the user, the results will be affected. Yeah, so it is best to use the principle of least square, or the method of so-called least square method. So we are going to use this method to get m and c accurately. Yeah? Whenever I say accurately, I mean it's better than the graphical method. So how to do that? So as I said, the method of, or the principles of least square says your error between your experimental value and your predicted value raised to the power whole square. So this is the how we define the error between the y value, in this case dependent variable obtained from experiments typically, and the one which is predicted using, say, the equation like y is equal to mx plus c raised to the power 2. So that error distribution, or that error function, that should be equal to minimum. Yeah, so how do you calculate, or how do you make sure that the error will be equal to minimum? So to ensure that the change in error with respect to the constants m, and the change in error with respect to the constant c, if that's equal to 0, then the error is said to be minimum. So in the previous videos I already explained how let's say you have error on the y-axis, and say you have different a values, and then if you plot error, you may see some curve like that may look like this, and this stationary point is nothing but the point where the change in a with respect to change in error with respect to a, this will be minimum. And to prove that this point is minimum and not maximum, we can even take second partial derivative of a with respect to e square, and then this value is positive, then this stationary point which is on this graph, follow the pin. So this partial derivative of e with respect to a, that will be equal to a stationary point that corresponds to the minimum, or in other words the error will be minimum at that particular point. So in this case, that stationary point will be equal to minimum, and that is something we can achieve when the partial derivative of e with respect to m and the partial derivative of e with respect to c, if both are equal to 0. So let's try to solve this using these principles of least square. So let's assume we have say I number of experiments. So let's write it that y, let's say x1, x2, x3, x4, and then say x of I, and then let's say the corresponding y values which is obtained from experiments are given by y1, y2, y3, y4, and then up to y of I. And let's say we use this linear equation or the straight line equation to predict the y values. So y1 predicted, this will be equal to m x1 plus c. y2 predicted will be equal to m x2 plus c, and so on. yi will be equal to, yi predicted will be equal to m x of I plus c. So from here we can calculate the error. So that will be equal to y1 minus y1 predicted, e will be equal, so similarly y2 minus y2 predicted, and finally for x of I here y of I minus y of I predicted. So let's expand this equation. So if we expand, it will look something like this. E will be equal to summation of y of I minus y of I predicted the whole square. Okay, in the previous table I forgot to put whole square, and then whole square. So that's how we define the error function. So the total sum will be equal to y of I minus y of I predicted the whole square. So let's write this equation. Say, so this will be equal to summation of y of I minus m x of I plus c the whole square. So this is how we define the error. So we have to differentiate the error with respect to a. So how do you differentiate? So this will be equal to 2 summation of y of I minus, so we are differentiating with respect to m plus c. So this will be multiplied by, so as we are differentiating with respect to m, so it will be multiplied by x of I. So let's expand this equation. So 2 x of I y of I summation, sorry, this will be multiplied by x of I. So this will be equal to 2 summation of x of I y of I minus m xi square plus c multiplied by x of I. So we know that this whole expression will be equal to 0 if the error is minimum. So then we can simply write this equation as summation of x of I y of I will be equal to m into summation of xi square plus c into summation of x of I. So this is something called as the normal equation. So I already boxed it, so I'm going to call this as equation number 1. So we have two constants m and c in this equation. So if we have to solve this equation, we need one more expression. So let's try to get the second expression, so that we can get by setting the condition dou e by dou c. This should be equal to 0. So if these two conditions meet, dou e by dou a and dou e by dou c, if both are 0, then error will be minimum. So let's try to take the partial derivative of the error with respect to c. So the error equation is shown here. So see the box. I'm going to differentiate this expression with respect to the constants, with respect to the variable c in this case. So in this error equation, x and y are the constants and m and c are the variables. So we are differentiating this error with respect to c. I'm going to do it. So partial derivative of e with respect to c. So this should be equal to same 2 summation of y of I minus m x of I plus c multiplied by, so we are differentiating with respect to c. So this will be equal to 1, and since you have a negative sign here in this equation, so this will be minus 1, and this is equal to 0. So how do you expand this equation? So 2 summation of y of I minus, you have a minus sign already here, so this, let's put it as minus 2 y of I minus m x of I plus c. So that's equal to 0, and this can be simplified as y of I minus summation of y of I minus m x of I plus c. So this whole term is equal to 0. Or, so what do I mean by this? So if let's say we have I is equal to maybe again 3. So in that case, x1, x2, x3. So we have 3 experiments, and then we have y1, y2, y3. The corresponding values obtained from the experiments, and then the error function, which in this case will be equal to y1 minus mx1 plus c, y2 minus mx2 plus c. So this is something dou e by dou a, dou e by dou a, and then you have y3 minus m x3 plus c. So how do you write this equation? So let's try to, so if you want to, so this is the change in error with respect to a. So if I have to take a sum of this equation, so how do you write? So dou e by dou a, so that will be equal to, I'm going to take y on one side, so it will be y, this whole term is equal to 0, so which means let me write it here. So y1, if we go back here, sorry, there should be a bracket here. So y1 minus mx1 plus c plus y2 minus mx2 plus c plus y3 minus mx3 plus c. So we can take y on one side because this whole term is equal to 0. So which means y1 plus y2 plus y3, everything should be equal to mx1 plus c plus mx2 plus c plus mx3 plus c. So how do you simplify this equation? So I'm going to write it like summation I is equal to 1 to 3 y of I, that should be equal to m multiplied summation of I is equal to 1 to 3, it will be x of I plus, we have 3 c's, 1, 2 and 3. So I'm going to say I multiplied by c, where I is equal to, I is, so in this case you have 3 i's, so I mean 3 experiments, so it will be I is equal to 3 in this case, so it will be 3c. So if we have I number of experiments, it will, this last term will be equal to IC. So if I write it in a general format, so this will be I is equal to 1 to 3 y of I equal to m I is equal to 1 to 3 x of I plus I of c. So if I have n number of experiments, so this will be simply y of I equal to m into x of I plus n multiplied by c. I'm going to box this equation and then I'm going to call this as equation 2. So this is something again called as a normal equation, and we already derived another normal equation which is given by summation of x of I equal to m summation of x of I whole square plus c summation of x of I. So this is something we already called as equation 1. So if we compare 1 and 2, what we have here, we have two constants or unknown parameters, and then we have two equations, so which is easier to solve now. So if we have x of x1, x2, x3, and then say we have y1, y2, y3 as an example, then from using this 1 and 2, if we manage to calculate summation of x of I multiplied by y of I, xi whole square, summation of x of I, then we can obtain equation 1, and then we can also get something equivalent to equation 2, and from equation 1 and 2 we can solve to obtain m and n. Yeah? So if we have an experimental data x versus y, then we implement equation 1 and 2, and then from there we can get m and c. And remember, this 1 and 2 were obtained assuming that, or using the method of the least square, or the both of these equations were obtained using the principles of least squares, which assumes error function which is defined as sum of the error square. This is something that changes with respect to the variables involved in the error function. So we will use these two equations and then we will solve some model problems in the next few videos. So in the next few videos we will try to solve experimental data that will follow a parabolic expression like y is equal to a plus bx plus cx square, and then some experimental data where x versus y follows the linear expression, so y is equal to mx plus c. So we will solve a few chemical engineering problems where you will have x versus y data. So the experimental data may follow either this equation or it may follow this type of equation, and then we will try to get the parameters involved or the constants involved in these equations using the method of least square, for which we need the normal equations which we derived so far. So thanks for listening.